Hi folks, this is Heath. Welcome back. We're starting the notes on injective and surjective functions. Let's go ahead and get started. What do we mean by injective? So let f be a function from set A to set B. We say that the function is injective if we can cancel the f's from any equation. If f of x1, f of x2 are equal, then we know that x1 and x2 are equal. Okay. This is not true for all functions. And let's see. For example, if my function is f of x is equal to x squared, then f of 3 is equal to f of negative 3, because this side is 9 and this side is 9, but I can't cancel the f's. And this is true, but 3 equals negative 3 is not. And so x squared is not an injective function. We can't cancel the f's automatically. This has caused us problems throughout algebra when we have to take a square root on both sides and we have to remember the plus or minus sign in front of the square root. Then and if we forget that, we miss points and that sort of thing. It has to do with not being injective. Sine is not injective. Sine of x is not injective, because the sine of 0 is the same as the sine of 2 pi, but I can't cancel the zeros. I can't cancel the signs. 0 does not equal to 2 pi. And so injective means we can cancel the f's. And so let's take a look at some examples. We want to show that the function e to the 4x minus 3 is injective. Okay? So we're going to assume that f of x1 is equal to f of x2. Okay? That means that e to the 4x x1 minus 3 is equal to e to the 4x2 minus 3. Are we allowed to take the natural log on both sides? And that cancels with the e, so we get 4x1 minus 3 equals 4x2 minus 3. If I add 3 to both sides, then I get 4x1 equal to 4x2. And then if I divide by 4, x1 equals x2. And so there's a chain of steps I can get to derive that x1 and x2 have to be the same based on the fact that e to the 4x minus 1 minus 3 equals e to the 4x2 minus 3. Okay? So this works. This is an injective function. Sine of x is not 1-to-1. We've actually already done that example. Sine of pi and sine of 2 pi are the same. We did 0 and 2 pi before, but pi and 2 pi are the same also. Both equal 0. But pi does not equal 2 pi. And so this is not a 1-to-1 function. Okay? 1-to-1 and injectives are synonyms. They both mean the same thing. Suppose that both of these functions are injective. then so is G composed with F. So here's what we're going to do. We're going to assume that F and G are injective. And let x1 and x2 be in A. So this is going to be just a direct proof. Suppose G composed with F of x1 is equal to G composed with F of x2. Since G is injective, this means we can cancel the G's, and we get f of x1 equals f of x2. And since f is injective, then we can cancel the f's and get x1 equals x2. And therefore, if G composed with f of x1 is equal to G composed with f of x2, then x1 equals x2, and so G composed with f is injective. Okay? The property of being injective is usually pretty easy to work with. It just says that you can cancel the function if it appears on both sides of the equation. And that's nice to be able to do. Surjective is a little bit tricky. We say that a function is surjective if for every y in the range, every y in B, there's at least one x in A such that f of x is equal to y. Okay? This doesn't happen all the time. Let's see. Natural log of x is not surjective because, for example, if y is equal to -2, there is no x that solves natural log of x equals -2. X squared is not surjective. Also for negative numbers. If y is equal to -4, there is no x that solves x squared equals -4. So to be surjective, no matter what y I pick, there's at least one x that solves the equation fx equals y. Okay, that's what it means. So we always have to find at least one x for this. So 2x plus 9 is surjective. Let y be any real number and assume 2x plus 9 is equal to y. Then x will be y minus 9 over 2 will satisfy the equation. Or we'll solve the equation. We'll say that. Since 2 times y minus 9 over 2 plus 9 is equal to, the 2's cancel, y minus 9 plus 9, and that equals y. Okay? So this is a surjective function because if you give me a y, I can find an x that will solve the equation. But what if this is the function from the integers to the integers and not from the reals to the reals? Okay. This is not surjective because 2 times an integer will be even, and an even plus an odd integer will always be odd. And so if y is any even integer, say y equals 12, then let's assume 2x plus 9 is equal to 12. Then 2x is equal to 3, but there is no integer that solves 2x equals 3. And so this is not a surjective function if we restrict the function to the integers, but it is a surjective function over the real numbers. Okay? If I have 2 surjective functions, then both of them combined together, composed together, are surjective also. So let's assume that f and g are both surjective, and let y be an element of C. Okay? Since G is surjective, then I can find some value in B that solves this problem. Then there exists some value I don't want to call it X because I have to go back a generation also, so I'll just call it B in B such that G of B is equal to Y. Since F is surjective, I can find something that will give me B. There exists some value X in A such that f of X is equal to B. Well, then G composed with f of X is equal to G composed with G of B, which is the same thing as Y. And so we have found an X that leads to the Y. Therefore, G composed with f of X equals Y. And that was what we needed to show, is that when we started with a Y, we could find an X that leads to that Y. And so G composed with F is surjective. All right. Let's talk about a new definition. A relation is just a subset of the Cartesian product. It's just a collection of ordered pairs in A cross B. And if I have a subset of the Cartesian product with the same product on both sides, A and A on both sides, then we call it a relation on A, on whatever that set is. So let's look at an example where we have a relation on N. So that means that both of these ordered pairs are in N, or both elements of the ordered pair are in N. And the requirement is that just M has to be a multiple of N. So is 15.3 in R? Yes, because 15 is a multiple of 3. Is 5.10 in R? Yeah, the answer is no. 5 is not a multiple of 10. What about 0, 0? Is 0 a multiple of 0? Yes. 0 is equal to 1 times 0. And so 0 is a multiple of 0. Is R a function? Well, to be a function, the first element in every ordered pair can only show up once. And this is not a function because not only is 15.3 in R, but 15.5 is also in R. So this R is a relation, but it's not a function. A lot of times we'll use a symbol to indicate a relation, like less than or greater than, are the two common ones, but we can also have less or equal to, greater than or equal to as well. That this indicates that the ordered pair is in the relation, the set of relation of that relation. Okay? All right, let's try example 8 here. We have a set of real numbers. We're going to use the less than or equal to symbol here to be the following relation. B minus A is 0 or positive. So does that give us a relation? Okay. We've used this symbol before. What this is saying is that, let's say 2, 7 is in R, or is in the set less or equal to, because 7 minus 2 is positive. And so we would write 2 less than or equal to 7 with the symbol in between. But this is what was going on. We're just saying that this describes a whole bunch of pairs of numbers that includes 2, 7. It includes 5, 5. 5, 5 is in this collection because 5 minus 5 is 0. And so we would write that 5 is less than or equal to 5. 8, 3 is not in this because 3 minus 8 is negative. Okay? Does this change the way less than or equal to works if we define it to be a set of ordered pairs, even if we write it using the way we do this? If our underlying model is that this is a collection of ordered pairs, does that change the way this behaves? Maybe, maybe not, but it gives us a way of proving things about relations by taking no matter what kind of relation we've got, we boil it down to a collection of ordered pairs. Okay? If A is a finite set, then any relation on A can be represented by an incident matrix. The incident matrix will be a K by K matrix in which we put a 1 in any place where that ordered pair is included and a 0 is 0 otherwise. We'll do an example here. My set is 0 through 7. Okay. So we have 8 columns and 8 rows in our incidence matrix. Okay. And the relation is A times B is a multiple of 5. So is 0 times 0 a multiple of 5? Yes, it's 5 times 0. Is 0 times 1 a multiple of 5? And the answer is yes, because 1 times 0 is 0, and 0 is a multiple of 5. 0 is a multiple of everything, so all of these are going to work. So let's talk about 1. Is 1 times 1 a multiple of 5? And the answer is no. 1 times 2 is not a multiple of 5. 1 times 3 is not a multiple of 5. 1 times 4 is not a multiple of 5, but 1 times 5 is 5. We look at 2. 2 times 2 is not a multiple of 5. 2 times 3 is not a multiple of 5. 2 times 4 is not a multiple of 5. But 2 times 5 sure is. And it's going to be that sort of pattern that I think if we don't want to take the time to work this out, anything in the row that corresponds with 5 will be a multiple of 5. And anything that's in the row of all zeros, or in the 0 row at the time, all of those turn out to be multiples of 5. But ordinarily, most products are not multiples of 5. Okay? So that's what the incidence matrix looks like. All right, let A be a set. We have a relation on A that's said to be an equivalence relation if all things, 3 of these conditions are true. XX is always in R. If I go back to this incidence matrix, it means that the entire diagonal is found in the relation. This is not an equivalence relation because I have some zeros along the diagonal. Okay? If this condition is true, that we say that the relation is reflexive. So less than is not reflexive, but less than or equal to is reflexive. Because any number is less or equal to itself. I can put the same number on both sides and it's true. The next condition, for an equivalence relation, if I have two different numbers, xy and yx, either they're both in R or neither one is. And we say that if that's true, then R is symmetric. And so equals is symmetric if 3 equals 3, then 3 equals 3. The order of the x and the y don't matter. But once again, less than is not symmetric. Um, 3 is less than 5, but then I can't switch the order and say 5 is also less than 3. Only one of those orders is true. And then transitive says that if x and y are related and y and z are related, then x and z are related. And less than is transitive. If x is less than y and y is less than z, then x is less than z. So less than is, we said it's not reflexive and it's not symmetric, but it is transitive. If A is less than B and B is less than C, then A is less than C. Okay. So let's look at this last example and then we'll wrap up. We have a set of integers and we have a relation on the integers where mn is in the relation if m and n are congruent mod 5. And we want to show that that's an equivalence relation. So we have to show three things. We have to show the reflexive property. We have to show the symmetric property. And we have to show the transitive property. The reflexive property is pretty easy. Let x be an integer. Okay. Then x minus x is 0, which is equal to 5 times 0. And so 0 is divisible by 5. And the reflexive property says that m congruent n has to be true. Well, if x minus x is equal to a number that's divisible by 5, and so x is congruent x mod 5. Okay? So symmetric, we're going to start out with, instead of just letting one number be in z, we're going to start let x be in z and let y equal z be in z. Okay? We're going to assume that x is congruent to y mod 5. Okay? This means y minus x is a multiple of 5. So y minus x is equal to 5 times k for some integer k. Then x minus y is equal to negative 5k for exactly the same issue, okay? And so y relates to x mod 5. Okay? So let's talk about transitive. This time we have to start with 3 letters. Let x be in z, y be in z, and z, little z, be in big Z. Okay? Assume that x and y and y and z are in the relation. What that means is that x is congruent to y mod 5 and y is congruent to z mod 5. Well, that means y minus x is equal to 5 times j for some integer j, and z minus y is equal to 5k for some integers j and k. Oh, well then z minus x is just z minus y plus y minus x, which will be 5j plus 5k, which is equal to 5 times j plus k. And so this is a multiple of 5. And so x is congruent to z mod 5. And so this is an equivalence relation. It is reflexive, and it's symmetric, and it's transitive. All right. Thanks for coming. Have a great weekend.